Hello, and welcome to the March 1992 edition of VideoTec. In this release, we'll be providing you with procedures and information on electrical troubleshooting and connector and wiring repair. We'll cover what to look for when making a visual inspection of connectors and wiring. We'll provide information on electrical test instruments. We'll do some electrical troubleshooting using the 6-step troubleshooting procedure. We'll provide information on soldering tools and materials. We'll show the correct way to splice and solder wires. And we'll perform some wiring and connector repairs. So let's start with connector and wiring inspection. When a vehicle comes in with an electrical problem, a visual inspection should be made of the connectors and wiring in the problem circuit. A connector could be partially disconnected. A connector could be damaged. For example, the latch could be broken. Or the connector could be cracked or melted. Be sure that both connector halves are fully engaged with a tight fit, that they are not damaged, and that all shields, latches, covers, and seals are present on the connector. Inside the connector, a terminal could be spread, or it could be pushed out. To properly check a terminal for spreading, you need to use a gauge. In some cases, you can make a gauge by obtaining the male pins from a connector repair kit. Another possibility is to remove a pin from the connector itself to check the terminals. We'll make a gauge for a 60-way connector using pins from the connector repair kit. 2 pins are required to make each gauge. Insert the base of a pin into each end of a piece of shrink tubing. Heat evenly with a heat gun until the tubing shrinks tightly onto the base of both pins. The shrink tubing provides a handle for the gauge. The gauge should fit tightly in the terminal. If not, the terminal is spread. And remember, whenever probing a terminal with a gauge or a test probe, be careful not to spread, push out, or otherwise damage the terminal. One way to inspect a connector for a pushed-out terminal is to see if the terminal is sticking out of the insulator. If the terminal is showing, separate the connector if you haven't already. Remove the locking wedge and push in the terminal from the back of the connector until it snaps into position. If it will not snap into position, remove it and inspect it for damage. When the terminal is back in position, install the wedge, making sure that it's flush with the face of the connector. If not, remove the wedge, clear the wedge cavity of obstructions, and reinstall. Another way to check for a pushed-out terminal is to make sure that the distance from the face of the connector to each terminal is equal. In addition to terminal spreading and push-out, terminals could fail to make contact for other reasons. To check for terminal damage, remove the terminal from the connector and visually inspect it. A terminal could be corroded, broken, bent, or discolored. Or there could be a faulty terminal grip crimp. If the terminals and connectors are okay, there could be a problem in the wiring itself. A wire could be cut, or the insulation could have worn through due to chafing, exposing bare wire. Check the wiring, making sure that it's properly routed and secured. Exposed or chafed wire is most likely to be found where it is unsecured. Electrical problems could also be caused by faulty ground connections. When electrical problems are present, always check ground connections to make sure that they're clean and secure. When troubleshooting a circuit, use the service manual wiring diagrams along with the 6-step troubleshooting procedure. We'll use this procedure later in the program, but first, let's take a brief look at some test instruments used in electrical troubleshooting. Test instruments for electrical circuits include the voltmeter, ammeter, and ohm meter. A voltmeter checks the electrical pressure or voltage when connected in parallel with the circuit. An ammeter measures the flow of current when connected in series with the circuit. An ohm meter checks the resistance of the circuit in ohms when there is no current flowing through the circuit. There are two types of meters, analog and digital. An analog meter uses a pointer and a scale to indicate a reading. A digital meter displays the number itself. Both types of meters have their advantages and their disadvantages. In general, a digital meter will have a higher impedance than an analog meter. A high impedance meter draws very little current from the circuit being tested. Digital multimeters are the best all-around meters, and the only meters to be used when working on electronic circuits. These meters may have an impedance of 10 million ohms and are referred to as 10 meg digital multimeters. In addition, many digital multimeters provide features such as an analog pointer in addition to the digital readout, and a smoothing feature that smooths out the reading when an input signal varies. Always use a meter with at least 1 meg of impedance when measuring circuits on today's vehicles. Although digital multimeters are the most useful, analog meters are still valuable for some applications. For example, when testing potentiometer-based components, like the throttle position sensor, the analog display provides a smooth reading of voltage increases and decreases. Analog meters are also recommended when performing self-diagnostic checks on MMC vehicles. For example, the self-diagnostic checks on the auto cruise control system use a series of electrical pulses to provide certain fault codes. These pulses are easier to read with an analog voltmeter. In summary, although an analog meter has some uses, the digital multimeter is the best all-around testing instrument for today's vehicles. Let's use a digital multimeter along with the 6-step troubleshooting procedure to do some electrical troubleshooting. When troubleshooting electrical failures, the 6-step troubleshooting procedure should be followed. The 6 steps are: verify the customer complaint, check for related symptoms, analyze the symptoms, isolate the trouble, repair the trouble, and verify proper operation. In this example, a customer complains that the heater blower motor doesn't work on his 92 Summit. First, we'll verify the complaint by checking heater operation. We turn the ignition on and the blower switch to high. We find that the blower motor does not work on high. Checking for related symptoms, we select the other blower speeds, and we find that the blower motor does not work at any speed. The next step is to use the wiring diagram for the heater circuit to analyze the symptoms. On the supply side of the blower motor circuit, we find that when the ignition switch is turned on, voltage is supplied to the heater relay coil, which is grounded at all times. The energized coil closes the relay contacts, and voltage is provided to the blower motor from the battery. The circuit from the battery to the relay contacts is protected by a fusible link and a 20-amp fuse. The circuit from the ignition switch to the relay coil is protected by a 10-amp fuse. On the ground side of the circuit, we find that when the blower switch is turned to high, ground is provided directly to the blower motor. When the lower fan speeds are selected, ground is provided through one or more resistors. Since the blower motor does not work at any fan speed, the resistor assembly is probably not the problem. To isolate the trouble, we'll break the circuit into 2 parts: the blower motor ground circuit and the blower motor supply circuit. We'll start by troubleshooting the blower motor supply circuit. After checking that the fuses are good, we disconnect the blower motor connector. With the ignition key on, attach the negative probe to ground and the positive probe to the blower motor connector blue wire, which is the positive terminal. being careful not to damage the terminal. There is no voltage reading at that terminal. Therefore, we've isolated the trouble to the supply circuit. Next, we'll check for voltage at the heater relay, located under the instrument panel near the driver's door. We remove the heater relay and find 4 relay terminals. According to the wiring diagram, terminal 1 is the power supply from the battery to the relay contact. Terminal 2 is the power supply from the ignition to the relay coil. Terminal 3 is the circuit from the relay contact to the blower motor. Terminal 4 is the circuit from the relay coil to ground. We check for voltage at the power supply from the battery to the relay contact. We also check for voltage at the power supply from the ignition to the relay coil. We find there is voltage at both terminals. Next, we'll switch the multimeter to ohms and check for continuity between the relay coil and ground. We find continuity. Finally, we check for continuity between the relay contact and the positive side of the blower motor connector. We find that there is continuity. Since all the circuits to the relay are okay, we have isolated the trouble to the relay. After the relay is replaced, we test the blower motor and find that it is operating properly at all blower speeds. Electrical trouble could also be caused by a faulty fuse. A common way to check a fuse is by removing it and visually inspecting it. A fuse with a melted center conductor is easy to detect, and the cause of the blown fuse should be determined. But the circuit through a fuse can also fail because of a poor connection at the fuse block. The preferred way of checking a fuse is while it's inside the fuse holder, using a voltmeter. With the key on, ground the negative side of the voltmeter and use the positive voltmeter lead to probe the fuse test tabs. If the circuit through the fuse is good, you should get the same voltage reading at both test tabs. Now, here are some tips when making circuit checks. Do not separate connectors if there's another way to diagnose the problem. Disconnecting and reconnecting connectors can cause pin and terminal damage or terminal pushout. Connectors should only be back probed when diagnostic procedures call for it. Use extreme caution when back probing, and avoid back probing radio and body controller connectors. When back probing weatherproof connectors, remove the end seal and replace it when the procedure is completed. When checking for continuity, you'll have to disconnect the connector and probe the front of the connector. But be careful not to force the probe into the terminal, causing it to spread. Never pull on wires to disconnect a connector. You can damage the wires and the terminals. Always pull on the connector itself, and be sure to unlock the connector latches. Do not overstress connector latches. Remove them carefully with your finger or a screwdriver. If they break off, the connector must be replaced. A digital multimeter can also be used as an ammeter for ignition off-draw tests. Depending on its components, a normal electrical system will draw from 5 to 30 milliamps from the battery. When the ignition is off, all electronic components have timed out, and the electrical system is in proper working order. If ignition off-draw is over 30 milliamps, the defect must be found and corrected. Testing for high amperage IOD must be performed first to prevent damage to most ammeters. To start, verify that all lamps and electrical accessories are off. Remove the ignition key and remove the engine compartment lamp bulb if there is one. In addition, deactivate all switches and accessories, which would extend the timeout of electronic components. For more details for the vehicle that you're working on, see Section 8A of the service manual. To test for high amperage IOD, install a test light having a cold resistance of 5 to 7 ohms securely between the negative battery post and the disconnected negative battery cable. Allow the components to time out. An alternative is to defeat the time out of a component by disconnecting it. Keep in mind that disconnecting a component may mask a problem if the current draw was caused by the disconnected component. When the test light dims or goes off, check for low amperage IOD by installing an ammeter between the negative battery cable and the negative battery post. Be sure to maintain battery connection with the test light until the ammeter is securely in place. On Monaco and Premier, hookup of an ammeter in the absence of a test light will cause a 50 amp surge through the ammeter because of the lighting module. When the ammeter is installed, disconnect the test light. If IOD is above 30 milliamps, the cause should be determined. Because IOD testing and diagnosis is different for all vehicles, be sure to see Section 8A of the service manual for the vehicle that you're working on. For additional information on IOD testing, see the September 1990 edition of VideoTec. One test you can do with a voltmeter will actually reveal excessive resistance in a circuit. This is known as checking for voltage drop. For example, to check voltage drop across the positive battery connection as it supplies current to the starter, connect the voltmeter positive lead to the positive battery post and connect the voltmeter negative lead to the positive cable terminal. When performing this test, the ignition system must be disabled. For vehicles with a conventional distributor, remove the coil's secondary cable from the distributor and connect it to ground. For vehicles with a direct ignition system, disconnect the ignition coil's electrical connector. When the ignition system is disabled, have a helper crank the engine and observe the voltmeter. A voltage reading over 1/10 of a volt during cranking indicates a poor connection. We've discussed electrical troubleshooting. Now, let's look at wiring repair. Although there are other ways to connect two wires, soldering is by far the best way. Soldering prevents oxidation, which is a chemical reaction between air and metal. Oxidation creates a high resistance to current flow. Soldering also adds to the mechanical strength of a joint. There are many varieties of solder on the market, but the type recommended for most electrical circuits is 60-40 rosin core solder, which is 60% tin and 40% lead. Tin is the metal that provides the shiny conductive coating created by soldering. Lead combined with tin reduces the melting point of the tin, making the solder safe to use on electrical circuits without overheating wiring and components. Rosin is used to prevent oxidation of the wiring during the soldering process. Rosin is contained in the core of some solder. It also comes in a tube or a can and is used when soldering larger gauge wires or when rosin core solder is not available. Never use acid core solder on electrical circuits. Acid core solder contains an acid paste in the core. Acid etches the wire, causing it to corrode. Corrosion creates a high resistance to current flow. Acid core solder is used to make mechanical repairs, like soldering brass tanks to radiator cores. A soldering iron or soldering gun is usually used for electrical soldering. A soldering gun heats up faster, but is difficult to use in confined areas. A soldering iron heats up slowly, but is lighter and easier to use in closed quarters. In addition to soldering irons, a heat gun has been found to be useful when soldering heavier gauge wire, since it applies heat to a larger surface. In addition to tools that provide heat, other tools are necessary during the soldering process. Diagonal cutters and wire strippers are used for cutting wire and stripping insulation. Needle nose pliers and needle nose vice grips are used for holding wire. And they act as heat sinks during the soldering process. Now, let's make a wiring repair using solder. When servicing wiring or wiring connectors, you may have to make a soldered connection between two wires. To make a proper splice, start by removing 1 inch of insulation from each of the wires. Place a piece of the proper size heat shrink tubing onto one of the wires. For wire from 10 gauge to 20 gauge, use 1/4 inch shrink tubing. The inside of the shrink tube is coated with a special sealant, which will come out of both ends of the tubing as the shrink tube is heated. Twist the wires together and you're ready to solder. Be sure that the soldering tool's tip is clean and tinned before starting to solder. Tinning aids in the heat transfer. Tin a soldering iron tip by applying a protective coating of solder to the tip. Heat the wire with the solder applied to it. A good procedure for a smaller gauge wire is to place the wire between the solder and the soldering tool. When the wire is hot enough, the solder will flow through the strands. Use only enough solder to bond the two wires, but make sure the solder goes inside of the strands as well as covering them. When enough solder has been applied to the joint, remove the coil of solder and continue to heat the joint to boil away any excess rosin. Now, remove the soldering iron and let the joint cool before allowing it to move. When cooled, the joint should have a smooth, semi-shiny appearance. One way to test a soldered connection is with an ohm meter. Touch the probes to the two wires that were soldered. Then touch the probes together. You should get the same reading if the joint is soldered properly. Now, center the shrink tubing over the exposed wire and heat the shrink tubing using a heat gun. Heat the shrink tubing until it's reduced to the diameter of the wire and sealant comes out of both ends of the tubing. That's the proper way to make a wiring connection. Now we'll look at some connector repairs. Some connector repair packages are available which eliminate the need to replace entire wiring harnesses when one connector is damaged. If a repair package is not available for a connector, the entire wiring harness must be replaced. Part numbers for wiring and connector repair packages are included in this month's reference book. The following publication also includes wiring and connector repair package information. TSB number 85391 provides instructions for wiring and connector repair. There are 3 basic types of connector repairs: replacing a damaged insulator, replacing a damaged terminal, or replacing a damaged connector as an assembly. Whenever performing any connector or wiring repair, always turn off the ignition and disconnect the battery. Let's start by covering the procedure for replacing a damaged insulator. For this example, we'll use a 60-way connector. Disconnect the damaged connector from the controller and remove the shield from the back of the connector. On larger connectors, it may be necessary to remove some of the tape from the harness in order to remove and replace one wire at a time. Remove the locking wedge from the connector by prying at the outer corner of the wedge with a small screwdriver or a knife. A small locking finger keeps each terminal locked in place inside the insulator. To remove a wire, move the locking finger away from the terminal with a small knife while pulling on the wire. Insert the separated wire in the same cavity of the new insulator, making sure that the terminal locks inside the insulator. To avoid mixing up the wires, it's best to remove and replace one wire at a time. Continue to remove and install each wire, making sure that it's inserted into the proper cavity. When inserting bus wires, make sure that they are twisted up to the insulator and that there are no other wires between them. A 60-way connector replacement package also includes cavity plugs for connector cavities without wires. When all the wires and plugs are inserted, install the connector locking wedge. Snap the shield on the back of the connector and retape the harness up to 1 1/2 inches of the connector. Reconnect the connector to the controller. And torque the 60-way connector bolt to 40 inch-pounds. Finally, connect the battery and verify the repair using the applicable diagnostic procedures. If a terminal is damaged on one or more of the wires that enter a connector, replace each damaged wire using the following procedure. With the ignition key off and the battery disconnected, separate the connector from the controller. Remove the shield from the back of the connector and remove the locking wedge. To remove the wire with the damaged terminal, move the locking finger away from the terminal while pulling on the wire. Remove enough tape from the wiring harness to be able to cut the wire about 6 inches from the back of the connector. Strip 1 inch of insulation from the wire. Find a wire from the repair package that best matches the color of the wire being repaired and cut it to the proper length. Strip 1 inch of insulation from the repair wire. Splice the two wires using the proper procedure and solder them together using rosin core solder. Center a piece of shrink tubing over the splice and heat it using a heat gun until sealant flows from both sides of the tube. Insert the terminal into the proper cavity of the connector and make sure that it locks in place. Insert the locking wedge into the connector. Snap the shield on the back of the connector and retape the wiring harness up to 1 1/2 inches of the connector. Re-engage the connector halves. Connect the battery and verify the repair using the applicable diagnostic procedures. In some cases, replacing the entire connector is appropriate. If this is the case, stagger cut all wires on the vehicle harness about 1/2 inch apart and strip 1 inch of insulation from each wire. Stagger cut the wires on the repair side wiring assembly to mate with the harness side wires, making sure that the overall length of the repaired wiring is the same as the original and allowing extra length for soldered connections. Strip 1 inch of insulation from each of the wires. Connect each wire, solder, and seal using the procedure shown earlier. When the joint is completed, tape the wire harness, connect the connector and the battery, and test the system. A harness repair package is available for the 7-way ignition switch connector on the 1993 Grand Cherokee. When servicing an ignition switch, always inspect the 7-way ignition switch connector for signs of corrosion, terminal discoloration, insulator damage, or loose terminals. To replace this connector, start by removing the trim panel below the steering column. Also, use a number 20 Torx head screwdriver to remove the lower cover from the steering column. Disconnect the ignition switch wiring connector from the ignition switch. Also, disconnect the key-in switch wiring connector, the clock spring wiring connector, and the multifunction switch wiring connector, which is bolted on with a 7mm hex head bolt. Remove the black plastic steering column wiring trough by removing the 3 clips that attach the trough to the steering column. Finally, remove the tape from the ignition wires. Then remove the tape from the wiring trough and remove the ignition wires from the trough. To make the splice, stagger cut all the ignition switch wires on the vehicle harness side about 1/2 inch apart. Make the cuts so that the wiring splices will be located inside the steering column wiring trough, toward the bottom of the steering column, where they're less likely to be damaged. Strip 1 inch of insulation from each wire. Stagger cut the matching wires on the ignition switch wiring repair kit in the opposite order as on the harness side, making sure that the harness will be the same length when the wires are soldered together. Strip 1 inch of insulation from each wire. After protecting the floor of the vehicle, solder the joints and cover the soldered joints with shrink tubing using the method described earlier. When the connections have been made, retape the arrowhead clip to the ignition switch wiring, making sure that there is enough wire length at the ignition switch connector. Now, reinstall all wiring inside the wiring trough and snap the new arrowhead clip into the slotted hole in the trough. Push the arrowhead clip through the new retaining washer. Retape the trough and all portions of the harness from which tape was removed. Snap the steering column wiring trough back onto the steering column with the clips provided in the repair package. Reconnect all of the wiring connectors that were disconnected. Reconnect the battery and check for proper vehicle operation. If all systems are operating properly, reassemble the trim panel and the steering column cover. It is possible that the terminal from the main battery disconnect may become spread or damaged and have to be replaced. To check the main battery disconnect for a spread terminal, use a carburetor gauge to measure the longitudinal slot in the sleeve. It should measure 25 thousandths to 35 thousandths inches. If it's larger, the terminal is spread. Also, visually inspect the pin on the male end of the battery disconnect to see that it's properly centered. If it's offset, it could spread the terminal. If either end of the connector is damaged and cannot be repaired, you will have to splice a new connector onto the harness. Since this is 6-gauge wire, the soldering procedure is a little more difficult. To splice a 6-gauge wire, strip 1 inch of insulation from each wire and slide a piece of 3/4 inch diameter shrink tubing over one of the wires. Apply rosin flux to the strands of each wire and interweave the strands of the 2 wires. Also, wrap a single piece of wire strand tightly around the joint to hold the 6-gauge wire strands together. This wire strand can be obtained from the 6-gauge wire that you're replacing. Wrap solder around the joint and place vice grips on both sides of the joint to act as heat sinks. Heat the joint with a 1500-watt heat gun rated at 700 degrees Fahrenheit. Use the heat gun's wraparound tip and lay the wire inside the tip with the heat gun vent closed. When the joint is heated, feed solder into the joint until it's filled and coated with solder. When the joint has cooled, center the shrink tubing over the joint and heat evenly until it shrinks tightly around the joint. This procedure can also be used to repair fuse links using the fuse link repair packages currently available. For more information on electrical troubleshooting, you can enroll in many of the electrical classes provided by Chrysler Service Training, listed in the Technical Training Course Selection Guide. Well, thanks for watching. We'll see you next month on VideoTec.